Okay, this video is for POW 4. We're going to be talking about alternative algorithms for multiplication. So on this solution video, I'm going to talk about the solution for problems 1, 2, 3, and 5. Talking about the explanations is going to be up to you. So first of all, 12 times 9 using the traditional multiplication algorithm goes like this. We line up the place values and we think about 2 times 9 is 18. We put the 8 ones down and carry the 1. And then we do 1 times 9 is 9, plus 1 makes 10. So question 2 asks you to think about what an expanded algorithm might look like. So expanded algorithms, the goal is really to represent all of the steps of the problem true to what's really happening. So when we do a problem like 12 times 9, we would ask ourselves, how much is 9 ones if we have 2 groups of them? Or alternatively, how much is 9 groups of 2 ones? Well, 9 groups of 2 ones is 18 ones. So we would put the entire 18 down. And then, instead of thinking what's 9 times 1, we think what's 9 groups of 10. And that gets us 90. And then we have to add them together at the end. So 8, and then we get 10 tens. So the real difference here is really just thinking about what the meaning of the place value is, that's not a 1, it's a 10. And so 10 groups of 9 would be 90. So how would you represent 12 times 9 using base 10 block drawings? Well, you can decide, we're going to do this 2 different ways. So you could think of it as 9 groups with 12 in each. Or you could think of it as 12 groups with 9 in each. So I'll do the first one and you can do the second one on your own. So 9 groups with 12 in each would look like this. So I'm going to draw 9 groups. And in each group is going to be 12. So I would represent 12 by showing a 10 and 2 ones. So remember, in our place block representation, our base 10 block representation, that's what 100 looks like, that's what a 10 looks like, and that is what a 1 looks like. And remember, we're representing those wooden cubes or the plastic cubes. So 9 groups of 12 in each. So 1, 2, 3, 4, 5, 6, 7, 8, 9. So, oh look, they look like little nervous faces. So if we thought about regrouping those, we could think of it as, well, there's 9 tens. Look, 1, 2, 3. So if I'm just counting the tens, I would go 10, 20, 30, 40, 50, 60, 70, 80, 90. So 9 groups of 10. I'll draw that so it looks like a 10 stick. And then there's also 9 groups of the 2 ones. Well, if we were to package these together, look, let me show this in a different color. I could put these 2, 4, 6, 8, 10. Those could all be repackaged into a new 1 or a new 10 altogether. So that would give me another 10. So I have 9 tens, now I just got a 10th 10. And then how many ones do I still have? These are the ones that are going to actually end up in my ones place. So I have 2, 4, 6, 8. It's kind of hard to see. Let me try a different color blue. 2, 4, 6, 8. So after repackaging these 10 ones into a 10, that gives me 9 tens plus 10 plus another 10 is 10 tens, which is the same as 100, plus 8 ones is 108. So I want you to try it. How would you repackage if you were thinking of it as 12 groups of 9? So in this one, you're going to have to draw out your 12 groups, so maybe like that. And in each group is going to go 9 little ones. And so draw those out, and then I want you to see what would it look like to repackage 10 at a time into a 10 stick. All right, and then in number 4 asks you, how are your drawings in 2 and 3 related, or how are your answers to number 2 and number 3 related? So it asks you to think about where do each of these numbers, like this one, the 18 and the 90, where do those show up down here? So maybe you could use a highlighter, or maybe you could use a colored pencil to show where does this 18 from the expanded algorithm, where is that 18 showing up in the drawings that you're creating with the base 10 blocks? All right, so you can do that on your own. And then now number 5 asks us, what would it look like to solve 12 times 90? Now, if we think about our base 10 blocks, in this one, we had 9 groups of 12. So here we have 90 groups of 12. So here's one of the really beautiful things about the expanded version of the algorithm. Which groups if you remember over here, we didn't do the ones first, we did the tens first. And we can do that here too. So we can think about what's 90, because there's no ones here. So what's 90 groups of 10? Well, that's going to be 900. So that's like thinking about if I have 90 circles drawn out, and inside each one is a 12. If I count all the tens up first, I'm going to get 900. I'm going to get 90 tens. So this comes from 90 times 10. And I skipped straight to 90 and 10 because, first of all, I just wanted to show how we were doing it over here. And because the partial products algorithm is impervious to commutativity. You don't have to go in any particular order. So then if we think about, okay, so we did the 90 groups of 10. What about the 90 groups of those little 2s? Well, 90 times 2 is 180 ones. And then we can think to ourselves, well, do we have any ones in that 90? So after we drew out 90 circles, were there any more circles? Well, no, there was only 90 circles. There wasn't 94 circles or 95 circles or whatever. So the 90 groups of 2 is just 180. We could add those together. We get 1,080, which we know should be, right? If 9 times 12 is 108, then 90 times 12 ought to be 1,080. I want to do one more for you in case you're still feeling a little shaky about the expanded algorithm. I'm going to do 92 times 12. Just so you can see what it would look like. So again, you can go in any order here. So let's start by doing 90 groups of 2. We ended with that last time. So if we started with that, 90 groups of 2 would give us 180. How about 2 ones times the 10? So this is those 2 extra. After we've drawn the 90 circles, we still have 2 more circles, and each of those has a 10 in it. So that would give us 20. So I've done 90 groups of 2. I've done 2 groups of 10. Now I'm going to do 90 groups of 10, which is going to give me 900, just like it did a second ago. And then I have 2 circles that have 2 in each. That would give me 4, 10, 9, 10, 11 hundreds. And if you compare that against the standard algorithm, we still get the same answer. 2 times 2 is 4. 1 times 2 is 2. And I put a 0 down. Why do I put a 0 down? Because now we're talking about groups that represent a 10. So we have 9 tens times 2. 9 times 2 is 18. And notice the 0 is already written for us because it's not 9 times 2 is 90 times 2 is 180. That's why we put that 0 there. 9 times 2 is 18. We carry the 1. 1 times 9 is 9, 10. And then we can add it together. So the only real difference is that in the expanded algorithm, all of the pieces of the place value are represented for what they actually mean. And one of the things that we spend a lot of time on in block 3 is talking about the area model. Maybe you remember this if you learned it. So I'm going to do this problem over here. But it's where we have thinking of 12 as 10 and 2, and thinking of 92 as 90 and 2. You would get this. And then if we add all those together, we still get 1104. So the area model is the way that the modules really teach students to think about what the multiplication algorithm is doing. Both of these, the expanded version of the algorithm and the area model, are both called partial products algorithms, because instead of thinking, because you're doing one product at a time, so you're solving it in partial amounts. In the base 10 block world, it means that you're adding them up separately. So you're doing the 10s first, then you're doing the 1s. So I hope that this made sense. If you feel like you could use some extra practice, whether it's with base 10 block representation or multiplication in general, please let us know so that we can help you out. This is a huge deal, especially in the 3rd grade and up. So if you've ever thought about, or if you're wondering whether you might be placed in a 3rd grade classroom, you need to have flexible use of more than just the standard algorithm for multiplication, because this algorithm right here, no, this one, sorry, the standard algorithm is not taught to students until the 5th grade, which means if you were teaching 3rd or 4th, or even 5th, this is not what you're mostly going to be teaching. You're going to be teaching these expanded versions and these model-based versions. So you need to be comfortable with how those work. All right, I hope you're having a good weekend, and I will see you in class.